time on Thursday, and we started looking at rapid flows. So let me just review what we did in the last class. Okay. Let's see if this works. Okay, so this is what we were doing. We had started, I told you about a very simple theory which helps us to calculate some things about rapid flows. And in this theory, if you look at the equations, they just look like the governing equations for fluid flow. The only thing extra is this loss due to inelastic collisions. And then we can get expressions for the pressure, the stress tensor, the viscosity, thermal conduction, thermal conductivity, and loss due to inelastic collisions. So, these are all explicit equations, and we have essentially enough equations to solve problems. So the first problem we looked at was cooling of a granular gas in zero gravity, where you have these particles that are colliding with each other, and with each collision some energy is lost. And so we assume everything is uniform and so forth, and the mean velocity is zero. And when we do all that, then we get this equation for the energy balance. The continuity equation and momentum balance equations are all satisfied identically. And we get this for the energy balance, which tells us how the temperature changes with time. And the rate of change of temperature is just dependent on the loss of energy due to inelastic collisions. And then we solved this, and we saw that if we write it like this, then it just is given by this. And then we wrote the same thing in dimensionless form, and we showed that how if you plot 1 by the square root of temperature versus time. I think there's a mistake in this formula. It should be T0 by T. So 1 by square root of temperature is proportional to time, which means 1 by square root of the kinetic energy of the particles is proportional to time. And if you remember, when we did all those problems with simulations and so forth, we found that. And in fact, if you do simulations, this equation is valid until longer times. Then when an instability occurs and the particles start to cluster like this. So each dot is a particle, and then after a long time they form these kinds of clusters. The second example we started looking was steady shear flow under zero gravity. The top wall is moving with a velocity u. Plates are separated by a distance h, and the fluctuation velocity v, or the temperature you can say, is 0 on both the walls. And then if we solve the momentum balance equations, we get that the shear stress is a constant and the pressure is a constant. And the energy balance equation gives us this. And the boundary conditions are that at u equal to 0, the mean velocity is 0 and the fluctuation velocity is 0. And at y equal to h, which is this surface, ux is equal to u and the fluctuation velocity is equal to 0. And in addition to this, we have the equation for the stress, which we can simplify and get an expression for dux by dy in terms of tau 0, s, which is a variable, and temperature is a variable. So here s and t are variables, everything else is a constant. And we have an expression for the thermal conductivity. Again, here the two variables are square root of T and S. And here also the variables are T and S. If we substitute for all of these things into this, then you see now you have one equation and there are, the only variables in this are S and T. So this is where we had stopped last time. And so we will continue and finish this example today, and then we'll talk about how we can study flow down an inclined surface. So we have done Newtonian fluid for flow down an inclined surface. So this will also tell us something. So let's do that. So I stop sharing this. And let's go to the lecture notes. Okay, so this is what we had done last time. We are looking at steady shear flow under zero gravity. And finally, we ended up with this equation. So let's continue from here. And so we are now in lecture number 24, and today's date is 27. So, we have this equation already, and now what we want to do is we need one more equation, because as I mentioned, there are essentially two variables. S, the spacing between particles, is a variable, and temperature is a variable. So the first thing I want to do is eliminate this S, and the way I can do it is through the pressure. So we know that P, which is just equal to, if you write down the equation for the pressure, it's just alpha rho B d T divided by S. And we know that this is just equal to a constant, which is P0. So since the pressure is constant, you see that S and T are proportional to each other. And so this gives us that S is just equal to alpha rho B d T by P0. Okay, so wherever there's alpha, so now let's substitute in this equation. So you get this 0 is equal to tau 0 squared eta 0 rho B t squared square root of temperature into alpha rho B d T by P0. So that is the first one. Then in the second term, we'll have d by dy, K0 rho b d squared into square root of t, and then we substitute for s, which is just alpha rho b dt into P0. So this essentially gives us the second term. And for the third term, we can do the same thing, and we'll get I0 into 1 minus E squared rho b into P0 divided by alpha. Now we can start simplifying. So just to make things a little easier, I'll just see this. Rho b cancels with rho b. Then d cancels with one of the d's. And if you do get rid of this, then I'm sorry. Then this becomes t raised to the power of half. Okay. Similarly here, rho b cancels with rho b, d gets rid of this, and this temperature goes away, and you have t raised to the power of half at the bottom. And again, in this one, rho b goes away, and then t becomes half. So now let's write the simplified equation down. So now this whole equation is only in terms of one variable, that is the temperature. So we get 0 is equal to, on the top we have just alpha tau 0 squared, and at the bottom we have eta 0 d into P0. So this is this term, and this is multiplied by t raised to the power of half. And then if you look at the second term, now here also we can see that a lot of simplifications can be done. So here we have K0 d P0 at the top, and at the bottom we have alpha and t raised to the power. And in the last term we have I0 into 1 minus E squared into P0 divided by alpha d into t raised to the power equal to 0. So you can see this whole thing is just a differential equation in terms of the temperature. Now, if I just divide throughout by, this prefactor, so that this equation, as well as this term, becomes a little simpler. So then I can write it down as d by dy of 1 by t raised to the power of half dt by dy plus, now I'm multiplying throughout by alpha and dividing by K0 into d into P0. So on top I will just get alpha squared tau 0 squared for the first term divided by eta 0 K0 d squared into P0 squared. And this is multiplied by t raised to the power of half. And then the last term is, since we are multiplying by alpha, and so this alpha goes away. And we have to do, so you have I0 1 minus e squared. Now multiplying throughout by P0, K0 and D. So this becomes P0 squared I'm multiplying by alpha and dividing. So I have to divide throughout by K0 D P0 squared. So P0 disappears, alpha disappears, and you will have at the bottom K0 D squared. So this is what I get. So this is a nice differential equation. And one of the things you see that this t raised to the power of half that comes here. Now supposing instead of writing it in terms of the temperature, we decide to write it in terms of the fluctuation velocity. So we know that t is just given as the fluctuation velocity v squared divided by 3. So then, you know, if this is the case, then dt by dy is just equal to 2v into 2v by 3 into dv by dy. So now if we substitute, so this gives us d by dy of, now you have 1 by t raised to the power half, so that is nothing but square root of 3 by v, and then instead of dt by dy we'll get 2 by 3 2v by 3 into dv by dy plus alpha squared tau 0 squared divided by root 3 eta 0 k0 d squared into p0 squared times the velocity minus I0 into 1 minus e squared times v. So this is what you get. And you know, you can see that there is a great simplification that happens. So you essentially end up with, here you will get 2, the v cancels out, so you just get 2 divided by square root of 3 into d squared v by dy squared plus alpha squared tau 0 squared divided by root 3 eta 0 k0 d squared p0 squared minus I0 into 1 minus this whole thing into v is equal to 0. So now if we get rid of this factor, then you can see that root 3 disappears, and then this is just multiplied by, multiplied by half. Okay. So if we write this as this governing equation as d squared v by dy squared plus, is this correct?
Yes, sir.
Omega squared v is equal to 0. And we expect that omega is going to be greater than 0. That because the term inside the bracket is always, we expect that, see, this term is the generation term. This generates the temperature, and this is the loss term. So we always want this to be larger than this, otherwise we will not get a steady state. If the loss term is larger than the generation term, then the flow will come to a rest. So now, if we, this is an easy equation to solve. Does anyone know the solution to this equation? So, does anyone know? Have you come across this type of second order equation where omega is a constant? So, waiting for someone to say something. You have to say either yes, I've seen this equation before, or you have to say no, I've never seen
Yes,
this.
sir.
Huh?
Yes. Yes, sir. We have seen this equation. Just integrating with respect.
I mean, the thing is that this second order ODE, so it's not that you can't just integrate it, but we know the solution to this. There are many ways of solving these types of second order ODE. How about the undergraduates? Yashmeet, have you ever seen this equation before?
It's a simple harmonic equation, right?
Simple harmonic. So you have seen it.
Yes, sir.
Which course?
No, sir, I just know it from previous classes.
It's
And all.
general knowledge.
Yeah.
How about Yash? Do you know? Where have you ever seen it in any course?
Yes, sir. We've actually seen it in a few courses before. I think transport phenomena as well, perhaps.
Maybe what was that? Okay, so let's assume that you have seen this, and there are many ways of solving this. So you can assume that V is of the form exponential e raised to the power of mx or something like that, and then solve it. But I'm just going to put down the solution directly, and we'll verify that it is correct. Okay. Supposing this is our solution, then we'll get dv by dy, where a, b, and omega, a and b are unknown constants. Omega, so we know what it is. This thing in brackets, this term is omega squared. So dv by dy is just going to be minus a omega cos omega y sine omega y plus b omega cos omega y. If we take the derivative again, then we'll get d squared v by dy squared is equal to minus a omega squared cos omega y minus b omega squared sine omega y. Now if we compare this equation to this one, we can see that this is nothing but minus omega squared times b. So that means every such solution with any arbitrary constants a and b is a solution to this equation, to the governing equation. So now we have to apply the boundary conditions to find out what is a and b. And here the boundary conditions, if you remember, are that v is equal to 0 at y equal to 0 and y equal to h. So if we apply the condition, the first condition, so we'll have 0 is equal to a, because cos of 0 is 1 and sine of 0 is 0. So 0 is equal to a, that is the first condition. And the second condition will give us 0 is equal to a cos of omega h plus b sine of omega h. So the first equation simply gives us a is equal to 0. And so we now have an equation which says b sine of omega h is equal to 0. So now what does this mean? Does this mean b is equal to 0? No. If we take b equal to 0, then we'll have a trivial solution, that is v is equal to 0. That means that there's no temperature. Then if there's no temperature, then there can be no flow. Of course, that is always the solution, but it won't satisfy our boundary condition that the mean velocity at the top surface is u. So we cannot have b equal to 0. So that means, since b cannot be 0, that means sine of omega h is equal to 0. And this actually tells us that now omega h cannot be just arbitrary, it has to have a specific value. And so this gives us that omega h must be equal to pi. And the reason I say this is because I mean, of course, I can write it as n pi, but what we expect that we'll not have a sort of fluctuating temperature profile inside the system. What we expect that at the most there can be one peak, and that's why we take only the first root. And so we get omega h is equal to pi. And so this actually gives us that omega is equal to pi by h. And so if we now look at this omega, it essentially tells us that tau 0 and p0 are not arbitrary and they are essentially related. And so what you get is half of this term, which is alpha 0 squared, tau 0 squared, divided by So I'm going to write it in a slightly different way. I just take out, if you see over here, we have d squared is common, so I'm going to take that out. And I guess k0 is also common, so I can take that out. So then this actually gives us that 1, I'm writing down omega squared. So 1 by 2 k0. Oh no, I won't take, I'll leave k0 in there. Anyway, it doesn't matter. So you just get this tau 0 squared by p0 squared into alpha squared divided by k0 eta 0 minus 1 divided by k0 is equal to pi squared by n squared. So this essentially gives us a relationship between the shear stress tau 0 and p0. So for a given velocity, your shear stress will be fixed if you specify what is p0. So this is one equation. And of course, the main thing that we wanted to solve was, of course, for the velocity v. So this is the equation that we want. And so we will have now that v is just equal to b sine of pi into y divided by h. So this is it. So what has happened is, through this, we have got one relationship between the shear stress and the pressure, and we have the velocity, but we still have an unknown constant, that is this constant b. So now we have to go further. And what do we do? What we would like to do now is to actually what we want to do now is to actually be able to get the mean velocity ux. And if I just go back in time, so all these things we have done. So the main thing I want to show you is this equation, and this is what we have to use. This equation is what we have to use along with this one to get an expression for ux in terms of the temperature, which we now know. So, if we actually just write that down again, so dux by dy is equal to let me just look at that formula again. Tau 0 into s divided by eta 0 rho b d squared. So this is nothing but tau 0 by eta, and eta is eta 0 rho b d squared into square root of the temperature. Correct? And then we also know that P is equal to alpha. Just above we have found out what is S, so we can use that expression for S. S is given by this alpha rho b dt by P0 So now if we substitute for both these things, we'll see that du by dx, dux by dy is just equal to tau 0 divided by so if we simplify this becomes t raised to the power of half, rho b goes away. So now what we are left with is tau 0, sorry, d also cancels from here. So you get tau 0 alpha, these are all constants, divided by eta 0 d into p0, and this whole thing into square root of t. And this, if we write in terms of the velocity v, fluctuation velocity, this gives us tau 0 alpha divided by root 3 eta 0 d p0 into v.
Sir, t cancels now. T raised to half.
No, but sorry,
There is some
what it was
t.
this was see, there was for s there was t, and
Yes.
here we have t raised to power half. So what I did was I cut out t raised to power half, and then I put this. I should have done it in red. Okay, let me do it. So this was the expression earlier, and then what I did was actually I said, okay, cut this out and make this half.
Yes, sir.
So then finally what I can get is that this is just tau 0 alpha square root of 3 eta 0 d p0, and now instead of v I can write down b sine of pi y by h. So you can see now this is an easy equation. This part is just a constant, and here now we can integrate it. And when I integrate this, I will get this is a simple integral. This is just going to be equal to minus of so this will give us something now. Integral of sine of this pi y by h is just minus of cosine of that into h by pi, correct? So this is tau 0 alpha b, this remains as it is, into h by pi into minus cos of pi h. This is okay, and then plus c1, which is a constant of integration. Now we know we have two boundary conditions. The boundary conditions are that ux is equal to 0 at y equal to 0, and ux is equal to u at y equal to h. So we have 0 is equal to minus tau 0 alpha v divided by root 3 eta 0 d into p0 into h by pi plus c1, correct? Since cos of 0 is 1. And then again you have u is equal to, now when I put y is equal to h, then this cos of pi, which is minus 1, so this becomes plus, so it becomes tau 0 alpha b so this gives us straight off, if I add up these two and then divide by 2, I'll get c1 is equal to u by 2. And then from the second one, I can get from the first equation, I already know that c1 is just equal to tau 0 so from the second one, what I will get is that instead of c1, I'll put u by 2 is equal to tau 0 alpha b into h by pi. So now through this second boundary condition, I can find out what is the other unknown coefficient, which is b. So now your b is just equal to what will I get b as? No real simplifications happen. So here I will get b is just equal to u by 2 into root 3 pi eta 0 d p0 divided by tau 0 alpha into h. So this is what your v is equal to. And I'll just give you one more equation, and that is that you can actually relate tau 0 and p0. So I have an equation now here in which, see, this equation relates tau 0 by p0 to all the other variables, including the height h. And then, so I can easily get what is tau 0 by p0 from here, from that equation, and that tau 0 by p0. So if I invert this equation, so I can get an expression for tau 0 in terms of all these other variables. Again, this is an easy thing to do, so I'll just write down the final result. So that just comes out to be 2 k0 eta 0 raised to the power of half. I think this you can easily figure out. And then you have pi d by alpha h. That's another factor. And then finally you have 1 plus h squared divided by pi squared lambda squared where this lambda squared is just equal to, so it's a so this lambda squared has a physical meaning, and this is the, so lambda is the sort of, you can think of it as something called the conduction length. So, you know, K0 is, will tell you, you know, how far some, how far these things will diffuse, and I0 into 1 minus E squared will tell you how fast the energy will dissipate. So if you start with some energy at some point and then it is being conducted, but as it is being conducted, energy is also being dissipated and it's disappearing. So the maximum length that, you know, the effect of this energy transfer, or that maximum length over which energy can be conducted before it is lost, is given by lambda. That's why it's called the conduction length. So by doing this, essentially what we are saying is that we can now write both V and U. So now you can see that I have an expression for B, and now I can eliminate tau 0 and P0, which are quantities that you don't know a priori. Shear stress and pressure, we don't know those things. But everything else is known in B. So we can actually write down B as just equal to U by 2. Let me just change this around a little bit. I can just write this as root 3 pi by 2 into eta 0 d divided by alpha h. Okay. And then what is left is P0 by tau 0. So then what you can get is this is divided by 1 divided by 2 K0 eta 0 raised to the power of half. And then this becomes alpha h divided by pi d. And then you have 1 plus h squared divided by pi squared lambda squared raised to the power minus 1. So if you look at this B, then several things can be cut out. This gets cut out, pi gets cut out, d gets cut out. And then, you know, you can say that this eta 0 goes away and you get this raised to the power of half. And here you have 2 square root of 2. So then finally this B is just given in terms of parameters that are all known to us as just root 3 by 2 root 2. Those are the coefficients. And then you have eta 0 by K0 raised to the power of half. And then you have 1 plus h squared pi squared lambda squared raised to the power of minus 1. Okay, so in this way we are able to get exactly all the things that we want. So if we are given H, so now everything is known in here. There's no unknown quantity. And then you have V is just equal to, I'm going to just rewrite that in terms of V only. V into sine of pi y by H. So this is one part of the solution. So this is for the temperature profile. And then you have Ux is equal to, now you see this, I didn't write down the final expression for Ux, but we can see that this whole prefactor, that C1 is just equal to all of this, but instead I can just put this equal to C1. So this entire prefactor over here, this is just equal to C1. So this I can write down as just C minus C1 into cos of pi y by H plus C1. And then we know C1 is just U by 2. So this finally we'll get Ux is just equal to U divided by 2 into 1 minus cos of pi y by H. Okay, so you have a really simple solution at the end for both the temperature and the velocity in terms of everything we know. So here is the constant B, and that gives us this fluctuation velocity. But the mean velocity is just dependent on U and H, that's it. And there you get a cost profile. There is a cosine kind of profile that you get over there. So this is really very nice. And then in addition to this, we have our expression for tau 0 and so forth given by this. Tau 0 by P0. So given any pressure in the system P0, I can get what is tau 0. And finally, you know, of course, if we know what is P0, then we can also get how the spacing varies because we know what is temperature. So we can get an expression for spacing as a function of y. I can write it down finally as S is just equal to alpha rho b dt by P0 now instead of T I can write down this as V squared by 3 P0. So here we can get this all the quantities, every quantity that we wanted. So these are, if you remember in the beginning when we started, we had 3 unknowns, and these were the temperature or the fluctuation velocity, the mean velocity, and the spacing. So these were the 3 variables, and we have been able to solve for them. Okay. So this essentially, with this I'll end the lecture, and I'll see you tomorrow.